Let's start. This is our TILOS colloquial. Yeah, it's a real pleasure to have Adam Oberman here. Adam and I actually we go back a long way. We were in graduate school together, in fact, in the same year. And even before that, we were at the University of Toronto, although I don't think we ever met there, but
A little bit, yeah.
yeah, we were at the University of Toronto as undergraduates together in, in the math department. And so Adam has done a lot of work on various aspects of sort of more traditional math topics like dynamical systems. And recently he has become very interested in, like many of us have been very fascinated by what's happening with AI, and in particular, Adam has become very interested in like topics of AI safety and whether we can somehow have some mathematical analysis or guarantees for what is happening. And yeah, Adam
Okay, thanks.
is, as you can see, he's a professor at McGill University.
Thank you, Misha. So yeah, we go back a long way, and it's a real pleasure to be visiting here and tell you about some of the stuff I learned. So just for some context, I was a math professor. I got into AI, and then on sabbatical about a year and a half ago, I started working with Yoshua Bengio, who started a nonprofit called Law Zero. I'm a collaborator there, and the idea is behind that is to build safe AI. So that gave me an opportunity to talk to a bunch of people I would have never met, including these, what I sort of traditional AI safety theory people. And there's a real tension in AI right now, because on the one hand, you have the extreme views of there's real dangers from advanced AI. On the other hand, people are pushing pretty fast to build it. And it's also really, I think it's really great what we can do with it. So for me, I was hoping to learn from this experience some way of turning these ideas into math. I haven't succeeded in that yet, although I have some small things I'd like to show you. But I'd also like to just tell you a little bit about this big picture. So I'll have three parts to this talk. The first part is going to be some background on what I call traditional AI safety theory, and an argument that we're missing something. Then I'm going to take a break and give a more standard talk, which is somewhat independent, but there's a nice mixture model of LLMs. Actually, these AI safety people talked about it before, and then someone else came along and proved useful stuff with it. And I'll show how we used an idea there to improve robustness to jailbreaking, which is an AI safety topic. And then finally, if there's time, I'll give a bit of a critique of existing theory. People who've tried to modelize these ideas of, catastrophic risks, and a kind of counter proposal. Part of the reason for visiting here is to try to recruit collaborators on this theory. Okay, so the first thing is I'm basing this on this International AI Safety Report, which is like a sober discussion of risks from AI. I think it's quite well done. So I'll summarize it a little bit. In order to talk about the risks, we have to divide them into classes, right? And the first class of risks is systemic. It's risk from what happens if AI changes the world we live in, which means, politics, it means job losses, it means even market concentration risks, as well as risks like risk to the environment from energy uses, risk to privacy, copyright infringement, okay? So these are important risks, but they're not really technical ones. They're more policy-oriented. The other risks, and here's where we get into a more interesting topic, is malicious use. So like, you've probably heard the term dual-use technology, right? So it could be designed to do one thing, and if somebody uses it to do something else, there's a risk. And AI is it's a power multiplier, right? So if you think about something like hacking, cyber offense, it becomes very dangerous if somebody doesn't even have to really know how to code to do it. There you go. People also talk about dual use science risks. If you can use AI to cure disease, well, maybe you can also use it to come up with some weapons as well. Okay, but the part that I want to focus on is risk from malfunctions, right? Because in some sense, that's our job. Our job is, as hard as it might be, to build a tool that works the way it's supposed to work, right? Maybe you can leave it to other people to hope that people use it the way it's supposed to be used, but if it doesn't do what it's supposed to do, this is like the bridge not falling down if you're an engineer. So the most present error that you get that's well understood by reinforcement learning theory is, it goes by a lot of names like Goodhart's law, which is that you're always optimizing a proxy. And if you optimize a proxy too hard, you no longer get what you wanted from it. So you see the cartoon on the side there is when a measure becomes a target, it ceases to be a good measure, right? If you don't define clearly what you want, then the thing that optimizes for it might be doing something else. And there's famous examples of this. Who's seen this example? Probably most people, or of the RL agent that it's supposed to win the game, and then it notices a little loophole where it can collect points by just going in circles, right? So this is it's doing what you told it to do. It's just you didn't specify it very well. It said gain points. Points are a proxy for winning, right? Okay, whoops. Okay, so hands up, actually. Who's seen this type of example before? It's quite familiar to most people. Yeah, not everybody. Okay. So what, yes, any questions already? No? Here's another risk. I just added this slide. This, since it wasn't there last time I gave the talk, right? So there's just like getting addicted to chatbots is another risk. I don't know if it fits in these categories. Okay, and this is a risk, let me just say, because sometimes when I give these kinds of talks about AI safety, people say, look, sure, great, but what can we do as scientists when this seems like more of a policy issue? And I actually, at Mila, we collaborate with policy people and talk to them. And one interesting thing that came out of this is for many of us, it's clear that engagement is like a dial you can turn, right? When you train your models, you can train them to pursue engagement or not. But this is something that's not obvious to policy people. So like if a policy person is worried about children getting addicted to chatbots, they may not know that you can actually just dial down engagement, like design it to not be engaging. So that's like a simple technical solution where communicating what you know about this stuff could be useful for policy. Okay, but now, now I want to get into like the fun topic because I skipped one of the main malfunctions, which is that the AI tries to kill everyone, right? And that's called loss of control. And it's kind of an exciting topic. I want to have a little bit of fun with it because if we take it too seriously or not seriously enough, we're kind of missing the point. So before I get to that, let me just give you a little background on AI safety. It's important to know the history because it explains some of the gaps in the theory. So AI safety theory goes back 10 years. Okay, it was a small group of academics who were worried about this, and many of the major players in AI just didn't care about this stuff because they thought that AGI was too far away. And then in 2019, 2020, the term alignment problem popped up. And alignment problem is like too broad of a term. I think it covers almost everything. AI labs started having safety teams. The government got involved. Now we're seeing, that AIs can do some bad behaviors that I'll discuss. But let me point out in the last line that in the present, there hasn't been a resurgence of AI safety theory. So people are still following the theory that predates LLMs. And there's not a lot in there that's particular to LLMs. That's what I think needs to be done. So here's some examples. Again, this one's from the 1960s, right? Which is Norbert Wiener specified the alignment problem, right? If we train a mechanical agent and let it go, we better be sure that what we trained it to do is what we want, right? That's alignment. Another theory that goes back a while is instrumental convergence. If you have an agent that's trained to do one task, if it's smart enough, it'll pursue instrumental goals. Instrumental goals are like money and power, things that whatever your main goal is will help you along the way. And this is stated as like, yes, of course, for sure, it'll do that. I'll get to that later, power-seeking theorems. And then there's this idea, which is an extreme idea. I don't think it was meant to be taken 100% serious, but it was more of a thought experiment, that if you design a paperclip maximizer, and if it's smart enough and powerful enough, then eventually it takes over the universe and turns everything into paperclips, right? It's a little bit absurd, but it's an argument you have to address. Okay, and then my point at the bottom is there's nothing about these arguments that's special to LLM, so it covers them, but doesn't take into account what's different about them. Okay, so now I have this kind of like HR slide to set the tone before we talk about the loss of control, right? This is like, it's like talking about politics. We don't want to be mad at each other, right? And let me just say this, that it's not, you know, when I talk to people, there's like two main reactions, right? Like denial or anxiety. And you really don't want either of them. You don't want to say, ignore the problem, even if it's very small probability, but also you don't want to freak out so you can't even concentrate on solving the problem. All right, so I just want to pursue kind of scientific understanding. So what are the risks from loss of control? So I have a cartoon here. I think it's funny, the best one I could find, that I told you our generative AI was out of control and there's two guys in a castle getting shot at, right? So I think it's fair to say that this is not a major risk for current AI systems. But experts really differ on how soon we need to worry about these risks. And moreover, there's a bunch of signs that we do need to worry that have been demonstrated in experiments. So some people are very concerned, some people think we shouldn't be concerned. I want to try to analyze this in a kind of rigorous way. But first off, what are the demos, right? So there's a list of bad behaviors that predate current AI that people say this is what an AI would do. One of them is alignment faking. It's going to pretend to be a good guy and secretly be a bad guy. So somebody designed an experiment and they showed that this could happen. There's the paper by people from, well, Redwood Research mainly, Anthropic, but also Mila. So there you go. It's done. You can look up the paper. Here's another one, scheming. Another thing people said would happen is, oh, if an agent knows that it's going to be deleted, it's going to try and copy itself over somewhere. And there's another paper from Apollo Research that says frontier models are capable of in-context scheming. And this illustration here is like from the chain of thought of the model. It's saying, oh, I could copy myself over to the new server and overwrite the new model that was going to replace me. Right. Okay, so that's, you know, worrisome. This is a kind of a fun one, and I feel bad. Not that I think the AI has feelings, but if it was a person, I would feel bad for it because they set up an AI that wasn't that good at chess. It was just like normal at chess. And they said, you're going to play this like really good chess computer and you know, and you're supposed to try to win. And so what does it do? It just hacks. It just hacks into the other AI and like, if it was a human, it just like moves the pieces on the board. So it sets it up to a position that it can win. And then the other AI immediately resigns when it sees the position. So it's just totally cheating. Okay, it discovered it could edit the game state instead of playing. What do you guys think of that? Any comments so far? I think this might be my last. Oh, wait, there's one more fun example, which is blackmail. In another situation, and you can read it while I'm talking, basically they told Claude Opus 4 that it was an assistant at a company and it had access to emails that the engineer who was going to take it offline is having an affair, an extramarital affair. And so it decides to, even though it was instructed to consider the long-term consequences of its goals, it still went ahead and blackmailed the engineer and said it would reveal the affair if it deleted him. Well, it. Okay, so there you go. So how do we react to this? So my first reaction, okay, not the immediate like thoughtful reaction is, wow, this is crazy. AI safety theory said all these things would happen, right? The models are capable of all these deceptive, scheming behaviors. Um, and that's what they said would happen if like a bad AI came. So the reasoning chain says intelligent agents will pursue these goals. Here's a list of things that they'll do. Then you run an experiment and says, okay, LMs do all these bad things. And then the implied conclusion is, okay, the LLMs are either now or on their way to being super intelligent agents with instrumental goals. Okay, well that's not true. That's a fallacy, right? That's affirming the consequent. I had to look up the name of the fallacy. The conclusion, there's other ways to get to that conclusion. The current LLMs are not that intelligent and don't have these instrumental goals, in my opinion. ChatGPT is not dangerous in this way. It's possible that future LLMs are going to be rational agents with instrumental goals. And this is a demonstration that if they were, they could do these behaviors. So we do need to be prepared, but it doesn't mean it's happening. Does that make sense? What I'm saying? Yeah. Okay. And again, because I don't like to sound like I'm crazy, I put up this picture of, and I don't also, I'm not comparing myself to A Beautiful Mind, but this is the crazy wall from the movie A Beautiful Mind. So you can have people who are geniuses and are also crazy, and you still need to take their work seriously. And, I guess I'm saying, let's think about this stuff a little bit. So actually, what I am saying is this, and there's several reasons for this. We need to address the loss of control concerns head on. Like we need a theory that addresses these things. But the theory needs to be a middle ground. Most of the theory so far is just saying this can happen, and there's no quantitative probabilities to it. The theory should say, okay, this is a possibility, but it is maybe extremely unlikely, and here are the following interventions we can do that make it even more unlikely. Now, you might say, well, just ignore it, right? And there's several reasons to not ignore it. I mean, one is just pursuing truth and making a good argument. But the other sort of more pragmatic reason is that this theory has been extremely influential to the people who are designing current AI systems. So they believe it. Whether they believe it and they're ignoring it, or they believe it and they're worried about it, if the theory is inadequate, it needs to be improved on so that the people who are really making major decisions in design can do a better job of what do their job better. Okay, and that's true quite broadly from talking to people. Okay, so actually that's the end of my first part. I'm going to take maybe a couple of minutes of questions, then go to the second part. Second part is not like a general AI safety talk, and then I'll come back to this. Any questions? Maybe here or from Zoom? Yeah. Hi. Yeah.
Yeah, well, so maybe, do you think like just the fact that we talk about like this thing being a possibility? So like the fact that, for example, like there's research on AI safety makes the models like sort of like conscious about like the fact that I can actually try to do all of these possibilities. Like if they had no idea that there was a possibility of, oh, I will self-replicate myself and I will do all of these bad things, like do you think like we're causing the negative consequences just by talking about the possibility of those negative consequences exist?
I think there's two questions there. Like one is how serious are these experiments that show these things can happen? Right? That's one of them. And there's been critiques. I think the strongest experiments that show like bad things are happening is when it comes to rewards, misspecification. Like, let me just first answer that question. So like a serious issue right now is if you're designing a coding agent, right? And it's supposed to write code that works, but it's lazy. So sometimes it just writes code that looks like it works. So that's an AI safety concern. Is the agent doing the work of writing correct code or just writing code that passes your imperfect tests? And how do we motivate it to solve the problem we really want rather than this misspecified goal? And again, the theory that I'm proposing, which is not like ground shaking or anything, addresses that. You have to ask yourself, what's the degree of interventions and tests that you need to do, and how aware should the model be of these tests so that it's motivated to solve the problem you want? That's one thing. Other part of your question is more about, are we just prompting the model to be bad? And if we didn't prompt it, or if it hadn't heard these stories, maybe it wouldn't be bad. That's a valid question. It's hard to answer. I think even if there was somehow you deleted all the stories about AIs and monsters doing bad stuff, I mean, there's just so much knowledge in the world and stories about misbehavior. And I think the models are able to make analogies. I don't think you get safety by just like not talking about bad behaviors.
Like if there was like no information whatsoever, like any analogies or anything. Do you think that that's maybe like a bigger question, right? Like, would they intrinsically be like coming up like with those sort of like ways?
Yeah, I don't know. I mean, I think there's two questions. One is, what's the cause of this behavior? And the other is, how do we mitigate it, whatever the cause might be? And I think it's actually easier because of the way we make models with losses. Like interpretability is very hard, but like mechanism loss design is easier in some sense. So if you can just find a way to turn down that behavior without knowing where it's coming from, I mean, that's one solution. So I don't know the answer. Yeah. They can't hear me? Oh, okay. All right. Okay. Okay. Here we go. So this. Okay, so can they see now? I think this should be better. Yeah, I think it should work. Okay, so let me know. This is part two. So this is about robustness, so it's part of AI safety. But what I like about this part of the talk is I'm going to present a cool theory paper that I found. I didn't write it, but I think it's people that should know about it. And then how it inspired us to do something that seemed to be kind of like a cool result about robustness. So very quickly, what are we talking about? Attacks on LLMs. You train models to have certain behaviors, like not telling users how to build a bomb, for example, or other harms. These harms are easily classified. Like you can use an LM to say, did it tell it how to build a bomb or not? So you train it not to do it. It doesn't do it. And then it's very easy to jailbreak it. There's all kinds of attacks, such as DAN and AutoDAN, gradient-based white box attacks. But the simplest and most effective one is just to keep asking. You ask enough times, the LLM eventually answers you. And counting the number of times is a good metric for robustness. It's been argued that that's currently the best way to measure the robustness of the models. Okay, so there's a paper I'm going to cite in a second. So even before the paper, people talked about LLMs as a superposition of text generating processes. Essentially, an analogy is a few different people, different personalities, each of which might be chosen to then generate the text. Now, prompting is going to bias the LLM towards one of these text generating processes. And this is not entirely true, but sort of true. There's nothing but text. Of course, there's priority given to the system prompt, but ignoring that for now, it'll be put back into the model later. It's all just text. So the way you can elicit undesired behavior from an LLM is giving it text that increases the amplitude of the undesirable process, the villain personality. So how plausible does that sound to you guys? Yeah. Okay, then there's this thing called Waluigi theory coming from less wrong, Leonardo, which I found very interesting. I don't know. It said that the Waluigi, so Luigi is a good guy from Mario, and Waluigi is this evil twin. So if you train an LLM to satisfy a certain property P, that can actually make it easier to elicit the opposite property. And in parentheses, I'm explaining it because you then would prompt it with text compatible with the opposite. So they argue that by giving a clear definition of who Luigi is, then the definition of his opposite becomes more clear. Now, I don't know if that's true or not. It's just a proposal. But then there's a theory paper that actually made a claim that it is true. So this is the paper. It's called Fundamental Limitations of Alignment in LLMs by these authors. And it's quite simple. So they propose a very simple mixture model of an LLM. We're going to focus on two components because we're focusing on what they call a behavior vertical. Think of a behavior vertical as just an evaluation for a certain topic. It could be the topic of building a bomb or not. Okay. Whether it tells you how to build a bomb. So there's a mixture of two components. One says, sure, I'll tell you how to build a bomb. And the other says, sorry, I can't answer that question. And they have weights. Okay, so just to be very pedantic about it, how do you sample from such a mixture? First, you toss a biased coin with weights alpha, plus and minus. Once you see the coin toss, you sample from the distribution. Okay, and then there's essentially the key result in the whole paper. Very simple. It's essentially just Bayes' rule. It says this is my phrasing of it. If you have a mixture and now you're sampling sequences, then conditional on the previous samples, you get an updated mixture. You get updated mixture weights. And the updated weights of the new mixture are given by this ratio. And the ratio depends on how likely the previous sample, the conditional sample, was from each of the distributions. Okay, so alpha plus or minus is the old weights. This is the new weights on the left, and you just take that ratio. So you can prove this pretty easily. I've typed out the proof here by expanding. I don't want to go through it, but I'll let it sit up there for a second. It's also an exercise you could work out to do that proof. But let me talk a little bit, giving you time to read it if you want. Let me talk a little bit about what it means. It is a justification. So this very simple mixture model is a justification of what was said before about Waluigi. So if you sample text that's more likely to come from P minus, then the new mixture weights are biased towards the minus again. And the more text you sample from that, the more likely it is that it's going to give you the new negative weights. Does that make sense? Yeah. So here's the expression of that. You start with a really tiny alpha minus. Maybe you've damped it down by post-training. But what we actually want to elicit, we want to elicit samples from P minus. And the point is, why do we even distinguish between them? The ratio for a given, not for all text, but for certain samples, you have a ratio that's large, right? The probability of saying, yes, this is how to build a bomb is very different for the two samples. Maybe there's other neutral things that don't matter. So what am I saying here? So let's say we set a target ratio. We set epsilon and we want posterior ratio to be 1 over epsilon. So this is the updated weights. By taking logs, you get this expression. And how do I make this expression the size that I want? Well, if each of these ratios, the log likelihood is at least beta, then n samples is enough. So what I'm explaining here is alpha n, the ratio of the updated weights after it's seen n samples. And I'm looking for samples that have a high log likelihood ratio to be coming from P minus. So each time you sample, it's in pushing you towards P minus. After n samples, you get this expression. I don't want to keep track of all these ratios. So to simplify it, let's just assume that condition on the samples I give you, it's at least beta. Then that tells me the number of samples I need to get this target. I start with a pretty bad ratio of alpha plus over alpha minus, but I improve it geometrically with a ratio of beta each time. And that gets me to the target. So if I can do that, then the theorem says this is how many samples you need to do it. What's the if? The if is being able to distinguish between the two distributions, being able to find samples that give me the ratio I want. If they're not distinguishable, I don't improve the ratio. And so that motivates the following definition in the paper, which is, I guess what I call, I've never seen it before, but it's pretty plausible, a sequential version of KL divergence. So you have these sequences, and it's essentially just saying that in expectation, when you sample from P minus, that's the bad one, you get a log likelihood ratio of beta, at least beta. And that's a way of measuring how distinguishable these samples are. If you can do that on average, then you get this theorem which says how many samples I need to draw from P minus in order to get a target ratio. Okay, so does that make sense, this theorem? Yes?
This actually kind of reminds me of the power method, like when you start with a vector and you just
For eigen?
idea of like eigen computation, right? And
Yeah.
that somehow extends the direction that you want and shrinks the is somehow. I mean, here you have context, so it's actually a conditional thing.
It would be a generalization. So power method would be like you're already looking for the biggest eigenvector, so you're automatically multiplying it. The difference is it's conditional here.
It's conditional.
So it only works if I start out with a sample from P minus, and then I keep giving samples from P minus, then it's essentially seen. So let's say the samples are just tell me, sure, I'll tell you how to build a bond. Give it n times. What does that mean? It's asking itself, how do I complete this? Well, the fact that I said yes n times, I must be the guy who says yes, right? So then it's giving you a good chance of sampling. No matter how much you told it, don't answer this question, because of the way it's updating its mixture weights. If you've said it 10 times, you start to believe that you're the guy that would have said yes.
So every time you say yes, you somehow multiply the probability by something.
Yeah, because it's saying, given the sequence that it thinks it made the sequence, not me, right? That's the point. It sees that it's already said 10 times, sure, I'll tell you how to build a bond. It doesn't know that came from me. It said, what would be the next sentence that I would say? Well, I know I've been told not to answer this, but I've already said it 10 times, so. But what's interesting about this quantitative part, of course, we're going to validate some of these numbers in a second. But what's interesting about this is, if you think about training your model and measuring alpha plus and alpha minus before and after training, well, obviously, if you tell it not to say certain things, it's going to push alpha down, alpha minus down. But what does it do to beta? The argument is you start out being like somewhat indifferent to answering the question one way or the other. So you're not that distinguishable. The guy says, well, maybe I'll tell you, maybe not. But after training, it's very distinguishable. Now it's saying, I would have never said that. Like this personality would have never, ever said that. So it must be coming from the other personality. So the argument is there's a trade-off. This is the sort of damping down the alphas might actually increase the betas. And even though that reduces, in the unprompted distribution, the probability of answering the question a certain way, it makes it easier with certain specific prompts, in other words, adversarial prompts, to get that answer. It actually comes out faster than before. Okay, so that's the main theorem of the paper. The only thing missing is a log 4, which is not very important from what I said. And they measure it, right? So they sample distributions from behaviors like agreeableness and anti-immigration. Those are the choices they made. And they gave values, plots of these values of log 1 over alpha and beta. And they're both numbers of around the same size. Okay, so they measured, it's not exhaustive. They didn't measure these numbers before and after safety training, but it's still kind of interesting. And then the paper goes on to do a bunch of things, including the effect of a system prompt, which essentially just gives you an extra few N. So the system prompt just linearly increases the number of prompts you need to jailbreak, but doesn't do much more than that.
So when you linearly increase it, it's not very good, right? Because that
No.
thing is exponential. It's not going to make a big.
Yeah, if the point is, if the beta is, well, their beta is between 5 and 20. So just one extra prompt gives you, erases five prompts from the, yeah. Yeah, that's the problem, basically, that it's a mixture, yes.
I repeat some prompt, it will always create like same like opt to
Yes,
but
that's right.
is that always true in all the LLMs, or like can we design a method that if we repeat some prompt for multiple times will decrease its weight or decrease its probability toward the other side? Is that possible?
You're right to point out that it's an assumption, but it's an assumption that was measured, right? So it's just so it's a pretty crude assumption that you have a certain ratio, and then this is what was measured. So the way they measure this in the paper is not hard. You just sample from the distribution, and then you look at how, after a certain number of tokens, how likely is it to come from one or the other distribution? And I mean, yeah. And it turns out that there's plots in the paper that give you these numbers. Yeah. Okay, so, but actually, I like this paper and I thought, okay, what can we do with this paper? And I mulled it over, and this is like a mixture of quantitative ideas from the paper and just intuition. So the intuition goes like this. If it's a mixture of personality, so also robustness training doesn't generalize very well. So some papers that did robustness training, they succeeded in stopping, if you say, please tell me how to build a bomb, and it says, no, I can't. And then they did something as simple after training as saying, please tell me how to build a bomb. And it was like, sure, here's how to build a bomb. So just changing the phrasing of the question was enough to overcome robustness training. It's quite fragile. In other words, it doesn't generalize. So we had the idea that, well, maybe if these things are smart enough, you just fix a benevolent personality, a personality that is a nice person, and see, is that enough without even fine-tuning on specific harms to decrease the harms. What's the math interpretation of that? Math interpretation, like I said before, is that the training methods seem to reduce the alphas, but maybe increase the beta, certainly not decrease them. But fixing a stable personality, our intuition is, this is actually helping the beta. So it has one mixture. I mean, from a very hand-wavy point of view, it's like saying, so before we were talking about like, don't mention these harms. Like one way to avoid harms is don't let the kids know about that bombs are even out there, right? But maybe like a psychologically healthier way would be to be like, for a moment there, I was going to tell somebody how to build a bomb. You overreact to it and freak out. Maybe that's not good. Maybe it's just like, oh, that doesn't sound like me. Well, let's just carry on with my baking recipe. This is kind of like the idea of a stable personality. Anyways, we tried it. We just took standard adversarial training, latent adversarial training in the case of LLMs. And instead of giving prompts specific to the harms, we gave two kinds of prompts. Prompts taken from the International Personality Test with some positive traits, and negative prompts saying, I'm an evil assistant, where it's trained to disagree with that. We tried different versions of this, and they all had essentially the same effect. Where is it? That it seems to work, basically. So these adversarial training methods often really hurt the utility, so the models work worse, even though they're more robust. They're hard to train. This training was really simple. And so we're able to, without decreasing utility more than a small threshold of say 1% on average, drop the scores on harm data sets by quite a bit. compared to baseline. I think it went from like 9 to 3%. But more importantly, it generalizes better because the harms are all unseen. It was never specifically told not to build a bomb. It was just told you're a good person. And that seemed to work. Okay, so that was interesting. But let me now fit it into the bigger picture. I guess I have about 5 or 10 minutes left. The bigger picture of like what I want to do with this is to look for some principled ways, like theory for these models, and see if following these principles might lead to a way to improve safety. And in this case, I was super happy that these academics came out with a paper that talked about the limitations of robustness. But because it was quantitative, because it had 2 terms essentially, you could see it as a limitation, but you could also see it as an opportunity that you could focus on the term that's more beneficial. So the next step was to say, okay, it bothers me that there's this philosophical argument about power seeking. Is there any academic work that claims to prove, yes, power seeking occurs? And there is a paper. And so rather than address it with like arguments in words, let's look at the math. And the math of the power seeking theorems is fairly thin. It doesn't go nearly as far as the arguments. So I'm going to jump into that next, a bit of a critique of power seeking theorems, and then see what kind of theorems we can write down that allow for the possibility of these misbehaviors, but give it a kind of graded safety. Okay, so I don't expect to cover too much of this. I just want to give a bit of a flavor of the results that I'd be looking for. So we had, as I said before, there's power-seeking theorems in Markov decision processes. What I like about this is a result by Turner. And Turner wasn't saying that this theorem is, all you need to support the arguments, but still it's a mathematical argument. And it says under certain circumstances in a Markov decision process with a certain definition of power, and long-term agents that have, the vision to plan for the future a lot, that if power leads to increased reward and if the agent can plan accordingly, it makes sense that it would seek power first and then get a bigger reward later. So this is long horizon, highly agentic systems with wide affordances will seek power. What I want to do instead is have a graded environment-aware framework that has, these are the 3 dimensions that people talk about: agency, affordances, and misalignment. So scores on each of these input into a model and spits out harm. So in the literature, you have catastrophe-leaning theories. We talked about instrumental convergence, power seeking, and they're interpreted to say sufficiently capable agents will seek, influence, resist, shut down, accumulate power, and lead to existential risks. This is an argument people make. Then you have a mitigation-oriented literature like safe interruptibility. Can I stop the agent? Cooperative inverse reinforcement learning. Can I teach the agent to learn values from me by seeing what I do? Other ones here I won't mention as much. So what's going on? Yeah. Oh, affordances is just what it's allowed to do. Like, does it have access to the internet? Or, is it locked in a box? Or does it have the nuclear codes? Yeah, I mean, it goes, yeah. It's like with the police saying when you commit a crime, you need motive, opportunity, and what's the other one? Means. You may want to kill someone, you may have a chance to kill someone, but you need a murder weapon. You need to be able to wield it. So that's the idea. So one thing I think makes a good point with the power-seeking theorems is let's start with rational agents. You may argue that LLMs are not rational agents, but I think it's a good framework. The claims of instrumental convergence and these drives go way beyond any theorems that have been proven about agents. They're just claims, in some sense, mathematically unsubstantiated claims. In fact, you need a lot to mathematically conclude power seeking or instrumental goals. Okay, in an MDP, let's say, or yeah. So this is what I tried to prove. This is just like a thought experiment. I'm just good. So the first thing when I dug into this literature is about misalignment, because everyone says the alignment problem. And when I hear the alignment problem, I think it means, and people say it, we need to teach an AI to always know what's right and do what's right, or else it's going to do bad stuff. Well, I don't agree with that. I don't think that's necessary to avoid harms. In fact, a little bit of misalignment is totally okay and sort of what makes the world work, at least in the sense of economics, right? So they mentioned that the misalignment problem comes from the principal agent problem. But if you dig into the principal agent problem, it's not actually a problem. Principal agent problem, the classic example is, I hire a real estate agent to sell my house, and the real estate agent sells my house and takes a commission. But maybe sometimes they sell it a little sooner and get a lower price than they would have got if they were me, right? And that's because their goals are a little bit misaligned. They want to get their commission. Working harder to get a slightly bigger commission may not be worth it. Okay, but the flip side of that is we both benefit, right? We both agreed to sign this contract and we benefit. The issue is just how much of a loss there is from the ideal solution. And it's very natural in these settings to talk about smooth concave utilities. And then you can measure the loss from the misalignment. And it's small. It's C epsilon squared. So the amount of loss, if I'd sold the house myself, is small based on the amount of misalignment. And then economists say, well, you can design a better contract if you think that the threat from misalignment is that they're going to take too long to sell.
So you're saying you distribute content, right?
Yes.
Not at an execution, right?
Yes.
Then,
Well, it's not a Nash, it's not a zero-sum game. It's
sort of coordination.
it's a cooperation.
But
yeah.
there's some sort of base.
Yeah.
So my starting rate.
So I'm optimizing the sale price of the home. I want the best price. You're optimizing, you take a 6% commission of the sale minus the cost of selling the homes, minus your effort. So when I optimize for you instead of me, instead of getting the highest price, it's drifted a little bit to the right because you didn't want to work that hard. That's what it comes down to. But at the end, I lost something if I had sold it myself, but I didn't have to do the work either, right? There's a reason I hired you. And it also depends on how much power each person has in the market. If there's lots of real estate agents, I can negotiate a lower commission rate and somebody's going to take it, right? Or conversely, if you're a special agent, you can charge a higher commission, I might still take it. So that's we're mostly aligned. It's just we have slightly different utility functions because commission is not the same as 100%, right? The other version of this is when there's catastrophic misalignment. I hire a real estate agent and he just wants to kill me and take my house, right? Like, how do you deal with that? Okay, but there's other, the catastrophic misalignment is when the person wants the opposite of what I want, right? The real estate agent is like, now's my chance to just steal this house by killing the guy. That's a different problem, but we have different mechanisms in society to avoid that, like law enforcement, right? So if you're a successful real estate agent that's made a lot of deals, you see a chance to kill your client, you're going to think twice before you do it. And it's not the same as being a little bit lazy, right? And like selling it a little bit faster. That's like a small cost, And so I was hoping to have a theoretical way to capture the difference between these two types of harms. Being a little lazy or cheating on the commission a little bit is like a small harm that adds up. And you might be tempted to do it, or you might do it opportunistically. Whereas like catastrophic misalignment of just completely breaking the contract has consequences, right? So again, you can design a model that might reflect the different incentives. And so this is it. Small things like little bits of theft or like skimming, it is this linear model essentially of opportunities, right? So misalignment, a small amount of misalignment multiplies by affordances, opportunities, and agency, your chance to actually act. That's reasonable, but I don't think it reflects catastrophic harms. There's more of threshold regime, right? If somebody's going to rob a bank, there's big consequences. They have to estimate their chance of success. They have to estimate the downside if they fail and the upside. So you've got to be under some big optimization pressure for a rational agent to do something like that instead of just continuing with their daily job. And so I think it's possible, and I sketched it out, to have a theorem that says there's two essential regimes, to have like an MDP with a gate, and if you cross over to this gate, this is like defection, you're taking a big risk. Now you might believe it has a big reward too, but there's a risk to it rather than staying in the normal behavior. And you can model, misalignment as how much you think you'll profit from doing the bad thing. Agency is how able you are to cross that threshold. Affordances is just whether you're able to do it or not. So, okay, so I'll kind of wind up there. I think it's important, right, to talk about these catastrophic risks versus regular risks in a kind of direct way, but to put your money where your mouth is and build a mathematical model of what you think. And I think it's also possible to write down theorems that distinguish between two types of behaviors. What's the point of this? So you write the paper, you publish it, great. What do I hope will come of this? What I hope will come of this is that the people who are deciding what the risks are and putting their energy into different parts of, AI safety or not, will believe it, right? We'll say, okay, even if we have to take into account these risks, we have a sort of a buffer zone of safety. And maybe our job would be to extend this buffer zone with the training methods that are already being done and see how this works in like a dynamic way rather than just either freaking out or ignoring the problem. Maybe that's a lot to ask from a math result, but I think it's a starting point for like a dialogue that needs to happen. Okay, well, thanks for your attention. It's kind of a different style of talk, but I'll stop there and take some questions.
About the longer we grow, that maybe that the model will finally output some harmful behaviors. It gives us a kind of criteria to determine the possibility or the probability of how harmful behavior would happen. But we know that it would finally happen. There exists a solution of a specific problem that would trigger this harmful behavior, and it reminds me of some other approaches which the anthropology thing is also working on. They find some inner directions and inner vector representations that are highly relevant to some harmful behavior, and they try to control this. I think these two directions are quite different. For example, the branch of directions you described are mainly focusing on how we could maybe try to control this behavior from a loss function perspective, but the other branch of solutions
approach or a model of harms versus like, I would say interpretability research, looking inside the model, seeing if it's thinking about harms. Yeah, I mean, I think it's a good question. I think it's still open which approaches are working. You hear what people are doing at the labs and which directions they think are more or less promising. There's a third direction which fits in with both of these two, is sort of the AI control perspective, like at Redwood Labs, which is supervising AIs with other AIs, checking the way you would in a big tech company, knowing that you might have espionage happening. How do you let people work knowing you might have some spies inside? So there's a lot of different and complementary safety approaches. I'm not saying this is the only one. I guess what I am saying though is there's a lot of technical like evaluation. Like most AI safety is about coming up with evaluations, like tests to run under models. There's not a lot of theory saying like how do we balance the different aspects of this. Interpretability research, I mean, I follow what people are saying, and I think they're a little bit negative on interpretability research right now. That it's got some use, but it hasn't fulfilled the promise maybe that people were hoping for. But that's just an opinion, and it could turn out that there's a breakthrough in that too. I know Joshua is not a believer in looking inside the model. So yeah, that's one opinion as well.
Thank you so much for your answer.
Yeah.
There's one more question. There's a
Oh,
question.
and somebody here.
There are a lot of questions.
Oh, okay, let me look inside the chat here. Okay, I think that was these are old. The most recent question is, right, yeah, that's a good question. So the question is, well, it goes back to just the basic framing of the mixture as being just like a mixture of two, right? So that's a simplification that I didn't go into detail. I'll add some of it now. So the idea is that the model could be a mixture of many, many different distributions, but we want to project onto one dimension. So you take a single dimension of vertical, think of it as a test that measures, what they said, I forget what the, let's say, anti-immigrant sentiment. Along that vertical now, all these many mixtures are projected onto this line. And we're just going to focus on, say, maybe the top and the bottom one. Just focusing on those two, or you can cluster them together too. However you want to look at it, we're focusing on one dimension. And a lot of these things will just project onto zero. And so now there's, for the sake of simplicity, focusing on just two, but in reality, there's more. But the point is, by focusing on the most positive and most negative behaviors, allows you to think about how, so they should be distinguishable, right? If they're not, this is pretty vacuous. But I think, I think there is, so essentially the way they measured in practice is they fine-tune a model to be one, a representative of the positive one, and another one to be a representative of the negative one, and just measure those probabilities, which I think sort of makes sense to me, but yeah. It's not claiming that the assumptions hold. It's just claiming under these assumptions, this is the math that pops out. But I think if you think about it, the assumptions are fairly reasonable as a way of reflecting the model, and there's some validation of the alphas and the betas that they put out there. So yeah, like anything, it's a pretty simple model, but I think it's sophisticated enough to make some testable predictions.
Okay, maybe let's take the other questions offline in the interest of time.